Hi, I'm Bennett Yip of the security team, and it's my pleasure to introduce you to our speaker today, Charlie Rice. Charlie Rice is a PhD student in the Department of Computer Science and Engineering at University of Washington, studying with Steve Gribble and Hank Levy. His current research focus is on improving the security and reliability of web content and web browsers, and this is the topic of the talk. In the past, he has also worked on models of wireless interference with David Weatherall. Charlie received a BA and an MS in computer science from Rice University, not named after him, but I'm sure you get this all the time. Where he worked with Corky Cartwright and Peter Drusel. At Rice, he was the second lead developer for Dr. Java, a widely used educational programming environment. Charlie?
Thank you, Bennett. So, hi, I'm Charlie Rice. I'm going to talk about our work at UW to make it safer to browse the web. And I'm going to focus on two topics in today's talk. The first is how we've seen that some web pages are being modified in flight, that is, between the server and the browser, and some of the implications that has, and how we can detect that with what we call web tripwires. And second, I'll give an overview of our ongoing research to design new web browser architectures to make it safer to run all the active code that's on today's web. And my work is motivated by the fact that it's really not safe to browse the web today. And you can see this in a pretty typical browsing scenario, where you might have several windows open in your browser, including some windows you've been to before, like a webmail client, maybe renting movies, and then some windows you haven't been to before, some pages like search results. Now, there's a lot of bad things that can happen in these situations. So first, one of these search results could try to exploit a vulnerability in your browser to install malware on your computer. And you've probably seen this in the news. There's lots of cases where some of these exploits appear either in banner ads or on pages to try and install software on your computer just by visiting a web page. Unfortunately, this is far from the only problem when browsing the web. So you've probably heard of cross-site scripting attacks. This is where an attacker has the ability to place their own script code on someone else's web page to do things like stealing cookies or modifying the page contents or leaking other private information from the page. Now, Yahoo Mail, for example, was vulnerable to a cross-site scripting attack in 2006 that meant that an incoming email could run script code as part of the mail client. And in doing so, it could then send mail to other people in your address book or send spam to other people. There's also what are called cross-site request forgery attacks, where pages can take advantage of the way that browsers handle credentials and try to abuse that. So say you're logged into Netflix in one window. Another window in your browser could send a request to Netflix in the background. And your browser will send your cookie, your Netflix cookie, with that request because it's going to Netflix's server. Now, in 2006, Netflix was actually vulnerable to an attack where another site could change your account settings just by sending one of these requests in the background. And sites have to go out of their way to make sure that these attacks don't happen in practice. Now, today, I'm going to talk mainly about what might be an emerging issue, which is that when clients request a web page, they might not get the page that the publisher intended, but instead some modification of that page, where, for example, an ad might have been inserted by their ISP. And so this could really change the page that they're looking at and might have some serious consequences. So in today's talk, I'm going to focus mainly on this last issue of how pages are being modified in flight, based on a recent measurement study we've done at the University of Washington. And I'll show how publishers can detect these sorts of changes to their own pages using what we call web tripwires. Then I'll take a step back and give you a broader overview of our work on creating a safer web browser architecture so that some of these other problems that I presented can also be addressed in the long term. And this is ongoing work that I'm doing at UW. OK, so in the first half of the talk, I'll cover what in-flight page changes we saw in practice and how we were able to detect them. This is joint work with Steve Gribble and Yoshi Kono at University of Washington and Nick Weaver at the International Computer Science Institute. This is a paper that will appear at NSDI this April. So we were inspired to do this measurement study based on a news article we saw last summer that suggested that some ISPs might be inserting ads into the pages their users requested. Now, we were pretty surprised to hear this, that this would actually be happening. And moreover, this implies that the ISP actually has some box on their network that is doing deep packet inspection and looking at the contents of web pages and then modifying them to insert ads or JavaScript or other content. So we were surprised by this, and we set out to answer the question, OK, how often does this occur in practice? So in this part of the talk, I'll show how we were able to detect these changes, the results of our measurement study in terms of what's being done in practice, some of the dangerous consequences we saw that came as a result of these changes, and then what publishers can do about it in terms of web tripwires. OK, so at a basic level, we realized we could detect these changes using some simple JavaScript code on our page. And we call this a web tripwire. It's a piece of JavaScript code we put on our page, which gets sent to the client's browser and runs there. And it does an integrity check on the page's HTML code. So it can see, has the HTML code been changed since it left the server? So for example, if an ISP had injected an ad that would have modified the HTML source code, and we'd see that change, and we'd display a message to the user saying this page has been modified in flight. We'd also report that change back to our server so that we could analyze it later. Now, we've put this online on a web page at vancouver.cs.washington.edu. And I'll leave that URL up there for the remainder of this part of the talk. You're welcome to visit it anytime you're on a network that you think might be altering your traffic if you just want to put them to the test. But to give you a little bit more of a feel of how the web tripwire works, we've built it so that it can support just normal, everyday pages where the client first fetches and renders the original HTML page. And there's no change at this point. But we've added a single line of JavaScript to the page, which in the background will then fetch a separate JavaScript file containing the web tripwire logic. Now, this web tripwire also includes an encoded version of the original page. You can think of this like a checksum or just a second copy of the page as a string that we have encoded in the tripwire code. Now, the idea is the web tripwire will then compare the actual page it received, the HTML source code, with what was in the web tripwire and see if there was a difference. Now, it's a little trickier than that because in the browser, you can't ask for the page's own HTML source code as a string because the JavaScript only has access to the browser's internal representation of the page in the DOM. And that varies from browser to browser in terms of what it sees. So we use a little trick where we just send an XML HTTP request for the original page, and then we'll get that back as a string. And because our page is cached in the client's browser, it doesn't even involve a network request. So we can then compare that string with what we expected it to be to see if there's any difference. OK. So to use this in a measurement study, we wanted to get lots of people to come visit the page, lots of people on many different networks, so we could see are some networks changing the page and some networks aren't, and so on. So we posted a story to Slashdot and to Dig and to some other news websites to try and get a large crowd of people to visit the page. And this worked pretty well for us. It ended up getting posted to these sites, and we got visits from 50,000 unique IP addresses over the course of about 2.5 weeks. So this gave us a nice data set to work from in terms of, is our page being modified in flight or not? OK, so what did we find? We honestly would have been a little surprised to see any changes at all. But as it turned out, we saw 657 of those IP addresses report some change back to our server. So that was about 1.3% of all the traffic that visited our page. Now, that was a lot more than we expected. Now, many of these changes are being made by client software. These are things like proxies that are installed on the client, which, when you think about it, some clients have ad blockers and pop-up blockers, and we'll see this sort of thing. We won't see changes made by browser extensions. Those are done within the browser itself. But if the client has some software installed outside the browser, we'll see that change. But we did see some changes that were made by agents in the network as well, including some changes made by internet service providers and enterprise firewalls. And what's more, we saw that there's really sort of a diverse set of incentives here for why people between the server and the browser might want to change the page, and that these incentives aren't always in line with what the publisher has in mind. So the publisher might be interested to know if their page is being modified in flight. So I'll give you a sense of that by walking through some of the categories of changes that we saw. And this includes changes made by ISPs, enterprise firewalls, client proxies, and even some cases of malware. OK, so we did see about 16 IP addresses that were affected by injected advertisements. So this is about 2.4% of the changes that were reported to us. And these are done by companies like Nebuad that contract with smaller ISPs to then inject a piece of JavaScript code into a web page, into every web page that a client visits. And then it does behavioral tracking so that it knows where clients have visited. And then it optionally displays an ad based on that client's browsing behavior. There's also some free wireless networks like MetroPhi and Lockbox. MetroPhi is here in the area, where you can get free wireless access, but they subsidize it by showing you ads on every page. And those ads are shown by actually modifying the page contents and putting the ad right into the page. Now, from the ISP's perspective, this is nice because it's a way for them to generate revenue off the people using their networks. On the same time, it's maybe annoying to many users, and it may affect publishers' own revenue streams when they display ads on their own pages. So their ad may not be at the top of the page anymore, or we don't know if there's been any cases of ad replacement, but that would certainly be a serious case. Now, another growing concern here is that this may be a trend that is increasing. Since the study, we've seen some more companies that are advertising this service that will talk to ISPs and say, we'll inject these ads into your traffic. And these include companies like PerfTech, Front Porch, Adzilla, and Form, which you may have seen in the news recently, is having some large contracts with major UK ISPs. So these companies are looking at deep packet inspection for web pages and then modifying them to show ads. Now, this isn't the only type of change we saw ISPs making. We saw another 30 IP addresses or so that were reported changes that were based on compression. So on low bandwidth networks, like cellular networks, the ISP might modify the web page to make it take up less bandwidth. An example of this is image distillation. They'll first ship you a low-quality image of an image, a low-quality version of an image, and then include some JavaScript. So if you click on the image, it'll send you the high-quality version. So these are being done in some networks as well. OK, so at the firewall level, we saw some changes being made by enterprise firewalls that were actually designed to increase security. So this may be a type of change that you might want to allow to your page in some cases. And a frequent case we saw was a product called Blue Coat Web Filter that would insert a piece of JavaScript code into web pages that would look for malicious behavior when it got to the client. So is the web page trying to change things about the address bar? Or is it trying to do anything that would make the page seem other than it is to the client? And so this is a case where it might actually increase the security of the page to allow some of these checks. And from the enterprise's perspective, this is nice because it might make the web a little safer for their clients. And from the publisher's perspective, it may also be nice to know if this is happening because they may be able to assign a lower risk to some clients than to others. For example, if you see a client who has some of these checks inserted, they're probably in a well-protected enterprise, versus a client who's browsing on a free wireless network who might have somebody snooping over their shoulder looking at their wireless traffic. So it may be nice to know if these checks are being done. OK, now most of the changes we saw were being done at the client. And this, like pop-up blockers and ad blockers account for about 70% of the changes that were reported to us. And these are done by products like Zone Alarm, which are personal firewalls, which might be designed just to block port connections in general, but they're also modifying web pages to prevent pop-ups. And it's done by dedicated products like AdMuncher and Proxometron. These are some proxies you can install that will modify the page to prevent ads and prevent pop-ups. Now, from the client's perspective, this might make some pages less annoying, especially if there's lots of flash ads and it's very distracting. From the publisher's perspective, on the other hand, this might impact your revenue if your ads aren't being viewed. Now, a final category is that we were surprised to find that we could detect certain types of malware using web tripwires. And for example, we saw one case where a client had adware installed. And this modified the page pretty heavily. So normally when clients visited our test page, they'd see a frame that had something like this, which is just a piece of text and a couple links in it. And what the adware did to the page was it added a few extra links, and I'll highlight those here in red, that had double underlines. And if you put your mouse over these links, then a new frame would appear that showed an ad that was targeted to whatever that word was. And so the adware was actually going through the source code of the page and turning some of these words into these little pop-up links. So that was a pretty invasive change in terms of the source code of the HTML. We also saw 2 clients that appeared to have been affected by worms. And our hypothesis here is that this is done using ARP poisoning. So we saw that some clients would report our page back to us as if it had an exploit injected into the top of the page. And what we think happened was there was another client on their local area network that was infected by a worm. And that client started sending out ARP packets to other clients on the network, saying, I'm the router, send your web requests through me. So now when this client requests a web page, it'll go through the infected client, who has a chance to modify it before it gets to the client who requested it. And when it does that, it has a chance to inject an exploit to try and spread the worm. We saw this in 2 cases. We also saw a case where a similar practice may be happening on the web server end, where an infected client in a server room was able to inject itself between the server and the outside world to inject exploits to all visitors to the site. Now, obviously, these sorts of changes are just there to help the malware authors, either to make money off the ads or to spread the worms. And they pose a clear risk to the user. So it's clear why you might want to know when these are happening. OK, so now I'll take a closer look at some very dangerous consequences that come as a result of these changes, beyond just why a publisher might not want it happening to their page. So some of these changes had unanticipated consequences. For example, they broke web pages that they were injecting content into. We saw in several cases that some of the in-flight page changes caused JavaScript errors on our page. So in some cases, it meant our web tripwire code didn't work. We just didn't get a report from that client. And we had to get feedback from the user saying that the JavaScript error occurred, and this is what was happening to the page. We also saw some of these changes affecting popular websites, like MySpace and several web forums. So you can actually find some of these sites by searching around, where a user's post to a site like MySpace actually has a little piece of pop-up blocking code in it. And it turns out this was injected by CA Personal Firewall, where it was trying to block pop-ups, but it was injecting the pop-up blocking code into the wrong part of the page, so that when the client posted a comment, the pop-up blocking code showed up in their post. And so there's some posts that just don't have anything to do with the comment, and then some users who are very confused, saying, why is my computer doing this to my posts? So it's sort of an amusing example of what can happen when you inject JavaScript code and that interferes with a page's execution. Now, unfortunately, it gets worse than this, because we also saw that there were some security vulnerabilities introduced by proxies that were modifying the page. And here I'm talking about cross-site scripting vulnerabilities, where an attacker then gets a chance to place their own script code on someone else's web page. Now, in the common case, this is usually caused by a bug on a web page itself in terms of the input handling. So if some input gets sent to the website and the website reflects that back to the user, if an attacker can hide script code in that, they're running script code on your page. And web developers go to great lengths to make sure that those bugs don't appear on their pages. They put in a lot of effort for this. Now, what we saw was that some proxies were modifying the web page and then injecting code that was vulnerable to a cross-site scripting attack. So then that original page would become vulnerable, even if it was otherwise safe. And this was done by products like AdMuncher and Proxometron. And I'll talk more about how the vulnerability worked in a second, but I want to point out 2 things here. One is that the web developers didn't really have any options. There was nothing that the web developers themselves could do about this, because the vulnerability didn't happen until after the page left their server. And second, for the clients who had one of these vulnerable proxies installed, the proxy was actually modifying most, if not all, of the web traffic that the client was receiving, which meant that most, if not all, of those pages became vulnerable to cross-site scripting attacks. And in the common case, this was most HTTP unencrypted pages. But in the case of Proxometron, there was even an option to have the proxy serve as the endpoint of encryption for HTTPS pages, so that they could block ads and pop-ups on HTTPS pages. Well, that meant that suddenly every page that the client requested, even encrypted pages, became vulnerable to cross-site scripting attacks. OK, and if you view the web browser as like an operating system, where it's actually running lots of programs from lots of different places, suddenly all programs are becoming vulnerable to attack. And that's sort of analogous to a root exploit, where every program you're using becomes vulnerable to attack. So how did this work? Well, in the normal course of execution, these proxies would inject a small piece of JavaScript code into every web page to try to block the ads and block pop-ups. Now, as part of that, these proxies would also include the full URL of the page in a JavaScript comment. Now, because it was a comment, it wasn't even affecting the functionality of the plugin. It just happened to be there. But unfortunately, the URL is something that the attacker can influence. So the attacker could place some script code at the end of the URL, either after a question mark to make it a server parameter, or after a hash to make it an anchor tag on the page. And then when the attacker convinces a user to visit that page, say by sending them a phishing email or by redirecting them from another web page, then that script code will get copied by the proxy into the body of the page itself. And then that code would run if it's formatted correctly, allowing the attacker to run code on that page. OK, so the first thing you could use this for is a phishing attack on some types of banks. Some banks use an HTTP front page that's unencrypted, has a login form for your username and password, and they don't switch over to HTTPS until after you've clicked the submit button. Well, in those cases, you can use one of these attacks to make that password form send the password somewhere else. But we built another exploit that shows how serious these attacks are. So we built a page that would detect if a user was using one of these vulnerable proxies, effectively by using a web tripwire. We'd look to see if it had injected code into our page. And if so, we would redirect them to Google. And then in the URL, we'd include an extra piece of script code. So that script code would then run on Google's front page and modify the search query form, so that when the user typed in a query, the attack code would propagate to the results page. OK, so now we're running JavaScript code on the results. And we can modify any of the results to point to different sites or to show different content. But what we did is we modified every outgoing link on the page to also include our attack code. So this means we're now running script code on every page the user visits in this browser window until they type in a new URL by hand or close that browser window. So this is a very serious exploit that we can watch what the user is doing and modify anything on any one of those pages. OK, so we've reported these vulnerabilities, and they've been fixed. So if you're using one of these products, be sure to upgrade to the newer versions that don't have these vulnerabilities. But it's really a demonstration of how much power these web page rewriting programs have, that it's effectively giving them root power over all of your web browsing traffic. And I also want to point out that by using web tripwires, we were able to detect these exploits, these vulnerabilities, more easily. And in these cases, it was because we could search for the URL of our own page within the changes that were reported to us. So those were the cases we could flag for further analysis, because if the change was including the URL, that means it's including something that the attacker has influence over. And we could look to see if it could then be further exploited. OK, so now let's talk about what options publishers have. So at a basic level, how should publishers react to the fact that their pages are being changed in flight? The first thing that comes to mind is probably just encrypting the page. If you switch to HTTPS, then your page won't be modified in flight, and some of these problems will go away. But you're probably also realizing that that's not a practical solution in all cases. You can't tell every web page on the internet to go switch over to HTTPS overnight just to deal with some of these changes. And it's also rigid in the sense that you may be disallowing some checks that you might want. You might want some of those blue coat web filter checks. You might want to support some transparent caching in the network, which would go away with encryption. And you might just want to avoid some of the costs involved in terms of the extra latency and the extra CPU overhead on the server. So we offer another option, which is less secure but can help you deal with the fact that these pages are being changed in flight. And that's that you can use a web tripwire, like we used in our study, to detect when these changes are being made to your own page. And again, this is just a piece of JavaScript code you can add to your page that runs in the background. And it's very easy to deploy because it doesn't interfere with the normal execution of the site. It's just a piece of JavaScript code that does this check and reports back to your server if it finds something different. Now, we've built this in the form of a configurable toolkit that makes it very easy to deploy on a normal web page. We've also built a service version that allows other websites to include a tripwire from our server and not have to have any code on their site. So then we can report to them if anyone has changed their site in flight. And in that sense, it's sort of similar to what Google Analytics does for normal website usage, where visitors might come to a website, and then Google Analytics records how they visit the site. It could also report if that page was being modified in flight. Now, the downside to this is that this is not a cryptographically secure approach. So if an adversary were in the network modifying the page in flight, and they knew about the web tripwire, then they could disable it. But we can try to make that difficult for them in practice by using code obfuscation techniques and other things to make it hard to, on the fly, tell if there's a tripwire, how it's working, and disable it so that it's not reporting any changes. So to give you a better sense of that, I'll walk through some of the trade-offs between using HTTPS and web tripwires. So HTTPS is really designed to ensure integrity and confidentiality, and it will prevent all in-flight changes to a page. So that will include some of these detrimental changes, but it may also prevent some useful services you might want for your page. Web tripwires won't prevent changes, but they will allow you to detect and analyze and possibly react by notifying the user or going after the people that are changing the page if an in-flight page change occurs. In terms of strength, HTTPS is cryptographically robust, whereas web tripwires may face an arms race if ISPs want to go out of their way to try and disable them. But we can make that difficult in practice by using code obfuscation. And finally, in terms of cost, HTTPS can be quite expensive in terms of getting a certificate, in terms of the computation, and the extra round trip times for setting up the SSL handshake, whereas web tripwires can run in the background. So they're very inexpensive to deploy, and it's just a piece of JavaScript. So we've done some performance measurements just to show that, and that we've built a web page and compared that to switching to HTTPS and switching to web tripwires. And in terms of latency, we don't affect the start latency of the page at all. The page will start to render at the same time. And the end latency is affected by a small amount as the tripwire runs. But again, that's just in the background. Versus HTTPS, which adds a large overhead to the start latency of the page. And in terms of throughput, the extra overhead for the server for web tripwires is just serving these extra bytes for the tripwire code and the known good representation of the page. Versus HTTPS, which has to do a lot more CPU overhead for SSL. Now, in these experiments, we were not using any crypto hardware to accelerate the HTTPS, and that could improve the situation for servers. But that would be another cost that you'd have to pay. OK, so an overview of this part of the talk. We've seen that web pages are being modified in flight for some subset of users, about 1% of the people who visited our page, and that these have had real negative impact, both from the publisher's perspective in terms of injected ads or annoyances, and in terms of security vulnerabilities. And so there's real incentive to know when this is happening to your page. And we've seen that these page rewriters can have very dangerous power, and that you should really put in a lot of security analysis before you use them. Finally, we've seen that web tripwires can be used to help publishers react to these changes if HTTPS is not a viable option. OK, so now let's take a step back. And that's addressed one of the threats I talked about at the beginning of the talk. And we have some ongoing research at UW to look at how we might be able to improve this situation by modifying the web browser itself to try and create a safer environment for running active code on the web. And this is joint work with my advisors, Steve Gribble and Hank Levy. OK, so how did we get to this situation where we have so many threats from active code? And part of it is that web content has really evolved significantly since the web's early days, where the web used to just be effectively static documents with HTML and images and maybe a little bit of script code. And the web browser could serve primarily as a document renderer that would just show you web pages and let you navigate between them. But things have changed significantly since then. Now there are many websites that have significant amounts of JavaScript code and other types of active content, Flash, Java, Silverlight, and so on, that are effectively forming programs running within the web browser. And these programs need to be isolated from each other, and the browser has to act like a runtime environment for these programs. In that sense, the browser has really become analogous to a small operating system that has to run these programs in a robust way. And unfortunately, today's browsers are not architected like operating systems. They're still built like document renderers, and that's not providing us a good environment for running these programs. So that has led us to a lot of these threats. And there's many more threats than just these in-flight page changes. We talked about the fact that we have browser exploits, we have cross-site scripting attacks, we have cross-site request forgery attacks, and even other types of interference between web pages within the browser. And we want to be able to support a safer environment for running these programs. So we really need to be able to support the fact that we are running web programs. And to get there, we need to have better ways to define what a web program is and how the web browsers are architected to support these programs. So we've boiled this down to what we think are a set of 4 architectural principles that need to be improved in today's web browsers. And we presented this at the Hotnets workshop last fall. And I'll walk through each of these before concluding. So first, we need to have better ways of defining the way web programs are specified on websites and in how they're supported within the browser. We need better ways of preventing unwanted code from running within a web program. We need to be able to isolate these web programs from each other within the browser itself. And we need to be able to apply uniform policies on what a web program can or can't do, regardless of what content type is within the program. So the first step is identifying the boundaries between programs. And on today's web, this is a little tricky because a web program is not just a web page. Obviously, it's a set of pages that can communicate with each other in the browser. And today's browsers use the same origin policy to say when pages can or can't communicate with each other. So if 2 pages come from different origins, then they're treated as isolated in the browser, and they can't talk to each other. But we feel that in the long run, this is a pretty fundamentally flawed policy, that it's not what would match your expectations of what belongs in a program or not. So for example, in some cases, it's too narrow. You may want to be able to include code from different origins in the same web program by creating a mashup, say, between content on MySpace and content on Google Maps. And current browsers make it awkward to do that safely because those pages come from different origins. At the same time, it may be too broad, that you may have lots of independent web programs all served from the same origin, like lots of user profiles on MySpace. But because those are all from the same origin, they're all getting lumped in the same box. At the same time, it's not a very secure boundary because it can be easily compromised. And you may have heard of DNS or binding attacks coming back into the spotlight recently, where origin is really just a name that's loosely bound to an IP address. And this means that you can go to a web page or a site like evil.com, and the first time you ask their DNS server what their IP address is, it says, oh, I'm this internet address, which is their real server. And then that page asks for a frame later on. And when you go back to evil.com and ask their DNS server what's your IP address, they report an address that's on your local area network instead. And so now your browser thinks that these 2 pages, one from the internet and one from your local area network, are part of the same origin and lets them talk to each other. So it allows an external site to spy on the contents of your internal network. So there's many reasons why we might want to move to something beyond the same origin policy. Within the browser itself, we think we need support for this new abstraction, this idea of a web program. And this is something, again, current browsers just don't know what a web program is. We're trying to infer it from the same origin policy, and it's just very awkward. And beyond that, we also need an abstraction for an instance of a web program running within the browser, because you could have multiple instances of the same program, and you might not want to prevent that from supporting that case. Now, the important thing here is that we need ways to assign exactly which resources belong to which web program. So this is which code, which documents, which images, and which data are allowed to be part of one web program and not another. So how can you define those boundaries? Now, this is still an open question, but we've started looking at new ways that you could define these boundaries. And one way you could do it is by using keys to define the program boundaries. So if you have a key pair, the author could have a private key that is effectively a secret that identifies your web program. And then the public key is served to the client. So to the client, a web program becomes that public key and a set of documents and resources that are signed by the private key. So the browser now knows which resources belong to which web program and when to distinguish them. Now, maybe you might not need to do this in all cases, but in certain applications where you really want strong boundaries between your web program and other web programs, it might make sense to support this as an option. And some of the nice properties are that a single web server can now host multiple web programs that are independent of each other just by generating multiple keys. Multiple servers could now host the same web program by sharing that private key with other servers they trust. And there's no PKI required, per se, because we're not trying to say who's providing these web programs, just that this web program is separate from another web program. Now, if you wanted to go that extra step and say who was providing the web program, you could do that, just as we do with SSL certificates. So this is one approach that we're starting to look at to see, could we do something better than same origin? All right, so the second step is preventing unwanted code in the browser. And this is familiar, again, from cross-site scripting attacks, where an attacker has the ability to place their own script code on someone else's web page, say by putting something in the URL and having that reflected back to the user. Now, we've also seen that even if you prevent all cross-site scripting attacks, that may not help in practice, because someone may change the page in flight and inject script code. In fact, 90% of the changes we saw in our measurement study were injecting script code into our page. Most of the in-flight changes were script code. So this is saying that web publishers really don't have control over what code is running on their web page if the page is being modified in flight or if cross-site scripting attacks occur. And so that's really a big concern. If you don't have control over your program, then how can you say what it's going to do or not do? And so from that perspective, we really need ways to authorize what code is allowed to run in your web program. And one approach that we're looking at to do this is using what are called script whitelists. And there was a project from University of Maryland and AT&T called BEEP, and another project that we've done concurrently at the University of Washington that looks at defining a set of hashes on a web page of every piece of JavaScript code that you want allowed to run there. And if some piece of JavaScript code appears on the page that is not in the whitelist, say by a cross-site scripting attack or by a in-flight page change, then the browser should know to ignore that. So it has a whitelist of exactly what code is allowed to run. Now, if we take this a step farther and say that a program is defined by a key pair, you could then sign that whitelist and say, make sure that in-flight page changes couldn't add things to the whitelist on the fly. And a whitelist could also be more difficult to modify than some of the other logic in terms of cross-site scripting attacks. We also want to generalize this beyond just JavaScript code to other types of active content as well, like Flash and Silverlight, because you don't want somebody to inject a Flash thing, which might be just as bad as JavaScript. Now, we have seen that there's some challenges here for dynamic pages. If your page is generated on the fly, and in particular, if JavaScript snippets on your page are generated on the fly, you might not know everything that belongs in the whitelist in advance. And so we've looked at some techniques that can help with that, too. In some cases, maybe by signing the whitelist or signing the pieces of JavaScript code to show that they're approved. OK, so now we need to have ways of isolating these programs from each other in the browser itself. And that is, even if these web programs, even if we solve the first two problems of defining what the program boundaries are and what's allowed to run in the program, you need to prevent other programs from interfering with your own web program. And so cross-site request forgery attacks are one example of this, where if you're logged into Google in the green page and some other page can forge requests to Google server as if it was coming from the client, we need to be able to prevent that. And we also need to prevent things like resource contention between pages. Because one page actively using the CPU or one page crashing the browser shouldn't make you lose your session when you're using other pages. And so we can get there by providing this better isolation between program boundaries. We can try to isolate the credentials between websites by having a notion of different instances of a web program. So if you're logged into Google in one instance of a web program and another site tries to send a request, then you could isolate the credentials between those two different instances. And you could take this a step farther. So you want to support today's persistent cookies and session cookies, but maybe you could have an option of a certain type of cookie that doesn't persist across instances of the page. So these requests will fail. You could also look at how the browser is architected and try to put these different web program instances in different processes. Because OSs already do this very well for existing programs, so that if one program crashes, it doesn't affect other programs. We have a tech report online that shows how you could do this in current web browsers just by putting content in different pages based on where it's coming from. OK, so finally, you want ways to apply uniform policies to what web programs can and can't do, regardless of what type of content they have. And here, if you have just a stock web browser and a web page with some HTML and JavaScript code, you probably have a fairly good idea about what that page can or can't do to your computer, just based on the browser's security model. But as soon as you start installing things like Java or Flash or Silverlight, all bets are effectively off, because those plugins all have their own security model that's independent of the browser. And not only might those have bugs in them, but they also have subtle differences between them. So when you start composing these different environments with different security policies, web pages can do things that they couldn't do before. And an example of this came up with DNS rebinding attacks. In a recent Stanford paper, they showed that a web page could make a DNS rebinding attack more effective if they combined JavaScript code and Java code, because each of those had separate DNS pinning policies, so that a request from JavaScript would make one request and ask what the IP address was, and the Java code would make a separate request. And then you became vulnerable because you were composing these content types. And unfortunately, the same thing is true with browser extensions. If you install things into Firefox like GreaseMonkey or AdBlock, you can also be subverting the browser's security model. And in fact, GreaseMonkey had a security vulnerability in 2005 that allowed web pages to effectively subvert the same origin policy. So at that time, there were no boundaries between web pages. And it was because of a pretty subtle thing GreaseMonkey was doing, and they had to go out of their way to fix that vulnerability. So when you start composing these environments that can violate the browser's security policies, you really can't reason about what a web program can or can't do to your computer or to other web programs. Now, we took a first cut at this with the Browser Shield project that I did at Microsoft Research 2 years ago. We were effectively trying to build an interposition layer for web pages by rewriting JavaScript code. And our goal here was to prevent exploits of known vulnerabilities in the browser. So if we know the browser is vulnerable to X, Y, and Z vulnerabilities, we could look at a web page and say, is it trying to exploit those? But we might not know if it's going to do that after the fact using JavaScript code. So we need to interpose on everything the JavaScript code does to make sure it doesn't exploit those vulnerabilities. Now, that gave us a nice policy framework for saying, OK, JavaScript code can do this, but not do this. And we could use it for any type of policy. Now, the way we built it was actually as an in-flight page change. So this might be one of those security checks that you might want to allow. This was nice from a deployment perspective, because it meant we didn't have to modify browsers at all. We could just deploy it at a proxy or deploy it on the server and say that anything that the client visits, or any clients who visit a site, get this protection for free. But on the downside, there were a lot of challenges to this. Some obvious ones are that we couldn't handle HTTPS pages from the proxy's perspective, because that was encrypted. It was hard to protect other types of active content that might not have been as easy to rewrite as JavaScript. And JavaScript wasn't easy to begin with. And importantly, it was hard to handle things like browser quirks, where one browser might handle malformed input in one way, and another browser might handle it in another way. And we'd have to predict exactly what a browser would do on a given piece of HTML to be able to enforce a policy decision on that. So this has led me to my current line of research, which is looking at building one of these interposition layers within the browser itself. So you can say exactly what web content can and can't do to critical browser resources like the DOM, regardless of what content format it is. And we want to be able to enforce policies on these different types of contents. Now, we might want that not just for the DOM, but for other resources as well, like the file system and the network. So if we could get plugins like Flash and like Silverlight to effectively treat the browser as the system call API instead of the real operating system, at least for certain key types of resources, then the browser could enforce policies on those calls. And we could then have a better step of reasoning about what a web program can and can't do, even if it has plugin content. OK, so that wraps up the browser architecture part of the talk. And overall, we've seen that there are a lot of threats on today's web. In-flight page changes are one of those. And web tripwires can help defend against, or help detect when those are happening, if not prevent them from happening in general. But beyond this, in the long term, we feel we do need new browser architectures to make it safer to run all this active code and handle these threats. And we think that's going to involve having better ways to define program boundaries, authorizing what code's allowed to run within a web program, isolating these web programs from each other, and then enforcing uniform policies on what these programs can and can't do. So thanks, and I'm happy to take questions. Yes?
So about your page that was being modified in flight by ISPs and proxies, was there anything in that page that was intended to trigger modification?
So the question was, do we have anything in our page that was intended to trigger modification by ISPs? We didn't have specific things that tried to draw their attention, but we did try to make the page look realistic from a commercial perspective. So we had text, we had links, we had some meta tags in the page, we had some certain keywords that might draw their attention. An interesting thing is we also heard that some of these ISPs were targeting just .com pages. And so we actually served many frames on our test page from different top-level domains. We had a .com page, .net, .org, .edu, and so on, to see if these were being modified. And in our results, we saw that in most cases, it affected all of the frames from any top-level domain. There were some cases where it was just .com. And there were some cases where we couldn't determine what the policy was, but it was some top-level domains and not others. Anything else? Yes?
The interesting
Is that a
part...
microphone?
Hey, Brad.
Oh, sorry. OK. So for the safer browser architecture, we have a flag day problem, right? Because if you want to put program boundaries, these are just safety wraps that someone can remove in flight.
Yes, so in-flight changes will matter here. And there may be cases where you want to have the equivalent protection for HTTPS. Now, if your web program is encrypted with HTTPS, you have your server with certificate that the browser can identify. And it will be difficult for an in-flight, an in-the-middle agent to modify that without changing the server's own certificate. Now, in the general case, yes, in-flight agents may be able to modify these programs in flight. What we view is it's not likely to be in the best interest for ISPs and other parties to make real malicious changes to content in flight. That it's more likely they're going to be doing things to try and make revenue off it or do analysis. And maybe that's bad from a code analysis or a functionality perspective. You might break something on the page, but it's not likely to introduce malicious things. It's much harder for an adversary to actually get on that path between the end user and the server.
The one thing that completely puzzled me in your talk was the authorized code section, where you talk about the code being authorized by virtue of whitelists. Where do you imagine these whitelists come from?
Yes. So the idea is the web publisher would provide a whitelist for their own web page, saying, here are the scripts that I expect to be there. And this is really because there's no one else who's qualified to say what scripts belong on a page and what don't. This means that the publisher does have to know in advance what all those are, and the publisher would have to take steps to make sure that no one else could modify that whitelist. But we do think the publisher is the one responsible for saying what code is authorized. Another question?
With regard to what you said about the cross-site request forgery, if I understood correctly, you were proposing that when page from origin A makes a cross-site request to origin B, that the browser not implicitly provide the user's authorizing information regarding origin B. Is that correct?
That is one approach you could take that would likely break some of today's sites, the way that they use cookies and things like remember me or the fact that you're logged in. You could try to introduce this as either another type of cookie or certain types of cookies don't get sent on these cross-site requests.
OK, so the reason I ask is there's currently controversy with regard to future web standards with regard to new forms of cross-origin request.
Yes.
Some of those proposals, for example, the cross-origin XML HTTP request, carries authorizing information and proposes that servers have yet another ACL mechanism for approving them. And then there's, for example, the cross-origin JSON request that whose rationale is exactly that it does not carry any implicit authorizing information.
Right.
Can you say something about how your work on the current cross-site request forgery issues bears on evaluating these proposals for extensions?
So I think that based on how we've started to look at how sites are using these cookies, this is still ongoing work, that there are some types of cookies that you do want to send on these cross-site requests in general. I think in terms of these proposals where you're actually having one website request data from some other website, that I would tend to lean towards the not providing authentication credentials in those cases, because then that just gives websites another tool that they could try to learn things that they're not allowed to learn, and that you should really use another mechanism if you want to allow those credentials to pass.
Hi.
Yes.
So I was just curious, you seem to have started with the assumption that the in-flight modification of the pages is bad, and I mostly agree. I was just curious because the thought struck me that you made the point that one of the things doing the in-flight modifications is free ad-based internet. So if you just stopped it, you'd also be stopping that as a business model, and there just wouldn't be ad-based internet. And what are your thoughts on that?
That's right. So I think that there may certainly be other ways to support ad-supported internet, free wireless networks, that don't depend on modifying the contents of the page itself. There may be things you could do in the longer run of having at least frames that are not modified, and then showing ads in a different part of the browser that aren't modifying the content of the page itself, so they're still isolated. Or you could try to support it through other forms of ad display that are outside the browser window itself, the content part of the window. I don't have exact solutions to propose here, but I think that the idea of injecting content into someone else's web page has some pretty serious consequences, and that's probably not the best way to do it. OK. So thank you again.